We've seen several examples of special types of quadrilaterals so far, but we've restricted ourselves to the realm of parallelograms. Now, not every quadrilateral is going to have two sets of opposite parallel sides, and if you constructed a quadrilateral at random, chances are it actually wouldn't have any unique properties that would give it a special name, let alone have the unique property of having two sets of opposite parallel sides. Most quadrilaterals are just that. We call them quadrilaterals. But there are names that we give to certain types of quadrilaterals that aren't parallelograms, and that's what this video is going to talk about. In this one, we're going to see the definitions and properties associated with the last two types of named quadrilaterals. Those are trapezoids and kites. So let's go ahead and start with a trapezoid. A trapezoid is a quadrilateral that has exactly one set of parallel opposite sides. And that word exactly is incredibly important here, because it's not that it has at least one set of parallel opposite sides, which is sometimes how definitions of trapezoids are presented. It's that it has one and only one set of parallel sides. So in the diagram below, you can notice that the parallel sides in the top and bottom are marked as parallel, and in a trapezoid, this is what we call bases. If you've seen the area formula for a trapezoid, then you know that they're referred to as bases as well, but the set of parallel sides in a trapezoid, those are the bases. So go ahead, pause the video, copy down the definition of a trapezoid as well as the diagram below, come back when you're ready to move on. We can further refine our definition of a trapezoid, or rather the type of trapezoid that we have, if we insist, for example, that our non-parallel sides are congruent. They don't necessarily have to be. For example, we could have a trapezoid that looks like this, where we have parallel sides, but the non-parallel sides aren't congruent. If we say that that's going to be the case, though, what we end up with is a figure called an isosceles trapezoid, similar to how we name an isosceles triangle. Two sides of an isosceles triangle are congruent, non-parallel sides of an isosceles trapezoid are congruent. So go ahead, pause the video, copy down this definition as well as the diagram below, come back when you are ready to see the last definition as well as the first property of trapezoids. So you may have noticed that in an isosceles trapezoid, there's a lot that seems symmetrical. And the last definition that we have around trapezoids fits really well in talking about it with isosceles trapezoids, and that's because we're going to be defining base angles. Now, in an isosceles triangle, base angles are opposite the congruent sides. We can't really do that here in a trapezoid because we don't have angles and sides that are neatly opposite each other, but we do have angles that are constructed from the same base. So, for example, the angles at the top of the trapezoid are both constructed from the shorter base, and the angles at the bottom of the trapezoid are both constructed from the longer base, and these are the things that we call base angles. And base angles are split into pairs according to which base they are constructed by. So base angle pairs are angles that are partially constructed by the same base, and in an isosceles trapezoid, base angles are congruent, as you can see in the diagram here. Notice that the angles that are marked congruent are always on the same base. So we have the two made by the longer base that are congruent and the two made by the shorter base that are congruent. So go ahead, pause the video, copy down this property of an isosceles trapezoid, come back when you are ready to see the proof. Okay, so let's go ahead and look at how we might go about proving this. Now, like many other proofs, this proof that base angles of an isosceles trapezoid are congruent is going to involve drawing at least one auxiliary line onto our diagram. But it's going to be a different type of line than we've drawn for a lot of them before. So if you have an idea of how you might prove this or how we might go about it, go ahead, pause the video, work out your strategies, and see what you can come up with. If you're looking at this and just want to see the proof itself as we go, that is also totally fine. Just go ahead and let the video keep running. But if you'd like to pause it and try to work it out for yourself now, go ahead and do that. So, for the sake of space, again, I'm not going to copy down the given, but the given would go right at the top of the proof. Okay, so we know that AB and CD are parallel. We know that AD and BC are congruent. Well, that would be great if we could find a way of showing that there are some congruent triangles or some sort of other congruent figures that are here. And in order to do that, we're going to draw two auxiliary lines, one from point A down to DC that is perpendicular. We're going to call that intersection E. And one from point B that is perpendicular. We're going to call that intersection F. And so what we're going to say here is that AE is perpendicular to DC and that BF is perpendicular to DC. And those are both by construction, because we have just added a new set of lines there. Okay, so now we have some triangles that we can talk about, and our goal here is going to be showing that the base angles D and C are congruent. So we know that the hypotenuse of these two right triangles, AD and BC, are congruent. That's part of the given. We know that angle AED is congruent to angle BFC. And we know that because all right angles are congruent. And we also know, even though it looks like we have congruent angles at D and C here, they're just there because that's what we're aiming to prove. We also know that parallel lines are equidistant from each other always. So the lengths of the perpendicular segments that are made between two parallel lines are always the same. We showed that in a previous module. So in this case, AE is congruent to BF. And that's because parallel lines are equidistant. And I'm just going to abbreviate that there. Great. Okay, so far so good. So now we have triangles that have one congruent angle and two congruent sides. In this case, it's not a violation of congruence because they're right angles, so we can use hypotenuse leg as our congruence theorem. And then we can say that triangle ADE is congruent to triangle BCF by HL. And that means that angle D is congruent to angle C by CPCTC. Cool. That's one step of that done. Now, in order to prove that A and B are congruent to each other, we have a few different ways that we could do this. We could, which is the way that we're going to do it here, we could say, well, we have some other congruent corresponding angles in our triangles, and because AB and EF are parallel to each other and AE and BF are parallel to each other because they are perpendicular to the same line, that ABEF is a rectangle, and therefore EAB and FBA are both right angles. Therefore, because right angles are congruent and because the other pieces of the angles are congruent, angle A is congruent to angle B. So I'm not going to write out the full formal proof process here, more that I'm going to just sketch what that means. We are going to say that ABFE is a rectangle From that, we're going to say that because they both have right angles, that the two angles that create angle A and angle B. We can just call them angle 1, angle 2, angle 3, and angle 4. That angle 1 plus angle 2 is equal to angle 3 plus angle 4. And that will end up completing the proof that base angles of an isosceles trapezoid are congruent. There are a few more properties that we're going to see as a part of this video, none that we're going to prove, but just that we're going to go ahead and look at the definitions for as well as copy down. The first is that if you connect the midpoints of the non-parallel sides of a trapezoid, you get something called a median. Go ahead, pause the video, copy down the definition of median as well as the diagram, come back when you're ready to move on. As it turns out, the length of the median has a particular relationship to the two bases, and the median of a trapezoid is parallel to the bases and has a length equal to the average of the lengths of the bases. So if the short base or the long base has length x and the other base has length y, then the length of the median is the average of x and y, or x plus y over 2. Go ahead, pause the video, write this down, including the additions to the diagram that you drew for the median definition, and come back when you're ready to see the definition and properties of a kite. So as we said, the last type of unique quadrilateral that we have is a kite, and a kite looks actually exactly like you would want it to. It is a quadrilateral with two sets of adjacent congruent sides to give it something that we recognize immediately as a kite. So go ahead, pause the video, copy down this diagram and definition, come back when you're ready to move on. So two properties of a kite that are actually very familiar because we've seen them with a different type of special quadrilateral. We have that one diagonal of a kite bisects two of the angles of the kite, as we can see here, and it specifically is the angles that are made by the two sets of congruent sides. This is very similar to a rhombus, except that a rhombus has diagonals that bisect both sets of opposite angles. In this case, the kite just has a diagonal that bisects one set of opposite angles. So go ahead, pause the video, copy this down, what you see on the screen, come back when you're ready to move on to the last screen. And finally, we have that the diagonals of a kite are perpendicular. Now this is also important because a rhombus has the same type of properties that a kite has. So, saying that the diagonals of a kite are perpendicular, or the diagonals of a quadrilateral are perpendicular, or that one of the diagonals bisects one of the sets of opposite angles isn't actually enough to tell us whether the quadrilateral is a kite or a rhombus. So not every property is going to tell you immediately that a run-of-the-mill quadrilateral has a particular classification. That's why we have to be very particular about the types of things that we know. If we know all four sides are congruent, then we know it's a rhombus. But if we don't, we can say maybe it's a rhombus, maybe it's a kite, but we don't know for sure. So go ahead, pause the video, copy down what is on this screen, and then we'll be ready to end the video and move on to your skill and proof practices.